Oh, hi there. You just caught me taking a nap in the hammock. My name's Michael Futch. How are you? Well, this lesson promises to be a dream for you, and I'm guaranteed it won't give you any nightmares.
Right, with modeling out of the way, it's time to look at database applications. So here's the agenda. Talk about what is a database application, what are the common characteristics of a DB application, how are they built mostly, understanding the layers that are found in any application, but we'll specifically focus on a database application. And then we'll explore the ways that a database application can be architected based on those layers, and you'll see there are many of these. And then we'll dive a little bit into how you go about gathering requirements that are non-data requirements that you can use to develop your application around. So first and foremost, what's a database application? Well, any application that stores its data in a database management system can be considered a database application. These applications are data focused, and we take a design that is based on the data requirements, and we implement the database in a model first approach. So we focus on the conceptual data model and the logical data model, and then we might implement the database, and then we may build the application around the database. So mostly the features in a database application are CRUD operations that support user actions. So maybe a manager might add a product, and then a user might order that product, as an example. So it's very heavily focused around data-like activities. That isn't to say that there aren't some really interesting and complicated business logic that might be in the application. It's just that is not the main focus of a database application. It really is surrounded by the data. There's support for user and roles. So not only is it a customer, it's any customer. So when somebody signs up, they might be in the customer role, and then they'll see user interface based on their role. And usually there are screens and reports. So if you go back to a diagram that we saw earlier around the end user and a database, and the database, remember, consists of data and metadata. Those together form any database. And this could be in a database management system. It doesn't necessarily have to be in a database management system. And then we have our data management, which brings the data in and the information out. The database application is a user interface on top of that data management. So these guys have several different names. And what you see happening over on the right is this an example of a database application. This is one that's used to submit requests to a manager to take a vacation, for example. And then after the request is submitted, a manager can go into and look at the request and then maybe approve the request if they want. So this is an example of a database application. We also might call this a line of business application. So it aligns with a business function or a business method within an organization. It's also called a forms over data app, because if you look at what you see here, there's a lot of user interface that is directly related to the underlying data structures, the tables, if you will, and the data that goes in the tables. So that's why it would be called a forms over data app. And we take a model-driven, model-first approach to an app like this, because we first build the data model, then we implement that data model, and then we build, the application over the existing database. This is sort of the process that we use in the DBLC, the database development lifecycle, is to build that database and then build the application on top of the database. It only works if you obviously have captured the right data requirements and also the right functional requirements to satisfy the needs of the application. So you can't just build a database without thinking through what the application involves or needs. You have to still do that, but it certainly does take that data into account first, and then from there we build the application around it. This is very different from the way that a lot of other applications might be built that are not database applications, where there is mainly a focus on maybe UI or features first, and not necessarily a main focus on the data itself, even though all applications have data. So database application development software is software specifically designed for the purpose of creating and building database applications. So some database application softwares have a DBMS built into them, others do not. So imagine you're using a product that has a DBMS built in. You could build the database first and then build the screens and UI on top of the database. An example of this kind of platform might be Microsoft Access or Claris FileMaker Pro. These are two examples of, they have a database management system built in. They allow you to make tables and whatnot, and then build a UI on top of that. They are database application software products that have a DBMS built in. Not all of them do, though. So these are also called no-code, low-code development platforms. No-code, low-code means you don't have to usually write any of the plumbing that talks to the database. That's handled for you. You really are just modeling a user interface and then attaching that user interface to the underlying tables in the data. Lots of examples of this low-code, no-code development platform like Oracle Apex, Microsoft Power Apps, Google AppSheet, Amazon Honeycode. There's actually many out there. If you Google no-code, low-code, you'll find dozens of them. This is a huge movement right now, especially on the web and in mobile, and we'll talk about why that is more in a few slides. So examples with of a database management development platform with the DBMS built in. There used to be a lot more of these, but there are now a lot less. And again, we'll talk about that as we get into application architectures later as to why that is. And basically the reason is they don't scale. So if you want to do this, at the cloud level with mobile devices and things like that, being attached, having your development environment attached to a particular DBMS does not allow you to scale. And so things like Microsoft Access and Claris FileMaker, while they're really kind of cool and interesting and innovative products, they aren't really where the future is headed in this way. Now, Intuit QuickBase, this is really kind of interesting because it's built in the cloud and it uses a cloud. So it's a little bit of a different animal than the other two. These also have names like Rapid Application Development or RAD platform or RAD tool. A RAD tool, a RAD platform. A platform is usually a fully integrated framework, whereas a tool might just be one piece of it. So a RAD tool, for example, might allow you to build a screen and then it would tie it to the database. A RAD platform would do all of that plus user management plus menus plus that. So you may recall the database development lifecycle, and again, in the database development lifecycle, this gets you through to the point where you build a database. When we go to build applications on top of that database, we still may do some additional analysis and design around the user interface and screens that are necessary that come out of that. So when you're thinking about data models here, we are down here in implementation. We're thinking about the internal data model. So it has been built. It exists somewhere. It's in a DBMS. And now we're going to build an application around it, an end user application around it. As you saw with SQL, right? Your end users are not going to be typing in SQL statements. Like they're not going to type in an insert statement. They're not going to type in a delete statement or, even a select statement. we need to build a UI on top of that so that users can go in and do their jobs, if you will, and not have to directly interact with the DBMS. So that's a good segue into these database application layers, because remember, we're building an application and we want the application to be usable by our end users, but yet we do not want them to have to know any kind of code or programming or even be concerned about what kind of DBMS is being used. Okay, that should all be abstracted away from them. So every data-oriented application has these layers in it. It has a presentation layer, and this is where you build the user interfaces in the presentation layer. Then the business logic layer is the meat of the application. It is the transformational logic at the heart of what the application does. So in the presentation layer, you may have a screen where someone can enter their zip code to get the weather. And then the business logic would be the part that went out, got the weather from somewhere, from some service, right? And then you might take that weather data and then store it somewhere. So that's data logic. And data logic corresponds to the CRUD operation. So you're either going to create, read, or update, delete data. It's really not much more to it than that. Every data logic piece should revolve around these. There's some complicated data logic out there, but really it's just a segue into, maybe you read first before you update, or you decide to read, and then if it doesn't exist, you create, for example. And then at the end of this is the database. So again, going end to end, you might ask for a zip code, or you might read the current location off a phone, for example. And then once you get the application off the location off the phone, you may use that to say, all right, now I'm going to go out and get the weather for that location, and then I may store that information and then present it back through the presentation layer to the user and say it's partly cloudy and it's 70 degrees. So again, presentation layer, user interface concerns. We present the information. We have menus and ways to navigate through the app, buttons, icons. Like in this particular mobile app, there's a hamburger menu up here, right? We are all very familiar with that metaphor. This one just has a bunch of buttons. And then it also will allow us to capture data, and it also does some logic through validation. But that's about as thin as you can get in the presentation layer. Presentation layers can be built in the web as a web page. They can be built native. That means you would download and install it on your Mac or Windows and run it there. Or it can also be run in mobile, as this example over here, which has a map. This is like an example of something like a Zillow, where it's looking up various pieces of real estate in an area and then showing you what the house looks like. The business logic layer is a little more sophisticated, and this is really responsible for a lot of the transformational activities of the application. So the main transformational logic of the application, what it does, is in the business logic layer. This usually has to be written in a programming language, but as you will see, there are newer tools and techniques now which allow you to actually create a lot of business logic in the cloud without writing any code, just by dragging and dropping things together. Like one of the more popular ones is if this, then that. When this certain thing happens, I want you to take these following actions. And so these kinds of tools can be used to automate things without having to necessarily write any code to do it. So the two examples I have on the screen here, up this one, you've probably used something like this before, where you take a photo of a check and then it deposits that money into your bank account. So the actual act of taking a photo, that is a presentation layer concern, but then the photo itself goes somewhere, and then something reads that photo and extracts out the data for you. And that is, in turn, business logic. And then the data that it finally gets, that would go into a database through data logic, and that's how it ends up in your account. So that's a great example of business logic. Another more common example of business logic is a shopping cart. Like when you add a product to your cart, right? In this case, the e-commerce website keeps track of the things you have in your cart and how much is your order subtotal for, and then you can proceed to order the products that are in your cart. So that management aspect is a form of business logic, and it has heavy interactions with the data layer, as most of the business logic does. So going down further is the data logic layer, and the data logic layer is responsible for talking to the database. That's all it does. It's responsible for the CRUD operations on the database. Commonly, this is done in SQL because SQL is the language that most databases will speak. Most database management systems will understand in order to do these CRUD operations. However, if you were just writing to a file or writing to an Excel spreadsheet as your database, you could have to use a different kind of data logic layer, like you might have to make a call to an API or something like that to implement the data logic. So there's lots of different ways that data logic can occur, but that doesn't change what it is. It is really just a way to read data from your database or update data from your database, or update data to your database. That's basically all data logic is. So to sort of give you an idea of how data logic sort of flows and why data logic is important, imagine if we had a piece of business logic that talked to the database as opposed to a piece of data logic, right? So this business logic might say, all right, here comes a user. Do they already exist in the database, or do I need to add them? And if they exist, I probably need to update them. So this would be a lot of chatty talking back and forth between the business logic and the database. So the business logic might say, hey, does user 15 exist, Mr. Database? And then the database will reply back, oh, yeah, that user exists. And then your business logic says, well, okay, now I know I need to update them. So then it says, okay, database, now perform an update. And then the database now says back, okay, I did it. Where encapsulating data logic makes sense is some database management systems allow you to take this interaction and encapsulate it into the database itself so that the business logic doesn't have to be heavily responsible for this back and forth conversation, which you might think is not a big deal. But when you're architecting an application that's distributed, as we'll see, the business logic could be on one computer and the database could be, database management system could be on another. And this ends up being a lot of network traffic just to figure out if you need to update somebody. So next unit, when we get to database programming, we'll talk about how to implement data logic and why. At least how to implement data logic in a relational database management system. So at the very end of these layers is the database itself. And the database is the persistent store of data and metadata, as we already know. And it's the database is required because, as required, the database will handle concurrency and consistency issues. So it'll handle situations like two people are trying to edit the same thing at the same time and what should happen. If you don't use a DBMS, then you are responsible for implementing that in your own data logic. So that's one of the advantages of using a DBMS is it handles a lot of those features for us. And that's why people like to use DBMSs for their databases rather than rolling their own database. Okay. So here's another video that I put together for you. It's a demo of using the Northwind Traders database, and this is the application that was built in Microsoft Access that goes on top of it. And you can see I'm filling out an order here, and you notice how I fill that order out and it automatically generates the pricing and things like that. I pick a product out of here, and then I enter a quantity. It says there's not enough inventory. What do you want to do? Do you want to reorder? Yes or no? And I can put in a discount, things like that. So presentation layer, what you see. Business logic is, hey, guess what? You can't order two of them because there aren't two of them in stock, right? And some data logic would be the fact that, once I enter all this stuff in, it figures out what the total is for me based on applying the discount and stuff like that. And then obviously that data logic talks to a database. This information needs to be stored somewhere because when I come back into order 86, I want to be able to see the stuff I entered. Okay, so that's sort of how it all integrates together. All right, with a keen understanding of the layers involved in any application, that is the presentation layer, the business logic layer, the data logic layer, and the database itself, we can now begin to discuss various ways that applications are architected. And let me get my fat head out of the way here. There we go. And so when we're talking about database application architectures, we might want to define how these workloads function in an application. So We can say, are they divided over a network or are they all working together? So when in a typical application architecture, there are clients and there are servers, and clients request resources and servers provide resources. So for any given application, parts of that application may function as a service, whereas other parts of that application may function as a client. And this client server model is what sort of drives an application that runs over a network. So we do this, by the way. Why do we run them over networks? Well, if we don't run our applications over a network, then more than one user cannot access the service. So imagine Amazon, but it's not a website. How does everybody in the world go there and order their stuff that they need to order if it is not a website? If it was something that you downloaded and installed on your computer, then you'd be working kind of in your own little world, especially if it didn't talk over the internet back to something else, right? To submit those orders. So we take that workload and we divide it up amongst several computers so that we can achieve better performance through the distribution of the work. So these are known as multi-tier architectures, multi-layered architectures, client-server architectures. It's all kind of the same thing. So when you're looking at any application architecture, it's measured in terms of complexity, and at the very top is the least complex, which is monolithic. We're going to go through all these in more detail. Monolithic over distributed storage, 2-tier thin clients and fat clients, 3-tier, N-tier, enterprise service bus, and then the most complex application architecture is a microservices architecture. So we're going to run through all 8 of these to give you a better idea of the various ways that the same application can be architected. And by architecting that same application in many different ways, it provides us additional flexibility. So a monolithic application is where the client has all of it. The client has presentation, business logic, data logic, and a database. It's all in one system. It's obviously the simplest design. It's single user, single site. There's no scaling. There's no network involved. So imagine we take all of Amazon, we package it up, and you install it, you download it and install it to your computer, and you place all these orders, and it charges your own credit card. But how would it know how to ship you anything? I don't know, right? So some applications don't even work as a monolith, right? But because they can't communicate with each other or with a central resource. So classic monolith applications might be something like Microsoft Word, right? You download it, install it, and use it. It doesn't really talk to anything else other than itself. Imagine a to-do application that you download to your phone, and you can put those to-dos on the phone, but you get another phone, they're not there. Okay, or like you have on here, you can't view them on your desktop. Okay, that's a great example of a monolithic application. So one step up from a regular monolith is we take that data that's part of the monolith, and we store that over a network. We distribute that, so like we might take the data from the application and put it on like Google Drive. But then the rest of the application is all still there. And this is a little better than a monolith because now you get single user, but you maybe can use it in multiple places. Like maybe on my to-do app, I save the to-dos to the cloud in Google Drive, and then when I open up my iPad and use the same to-do app, it reads those to-dos from Google Drive. So in that way, all the presentation, business logic, and data logic is on the phone or the iPad, but the data itself is stored somewhere in the cloud, and it can be used in 2 places. Now, if there's a bug on this version, there may not be the same bug on the iPad version because that all the code, the data logic and the business logic and presentation, is in the client. So that's where it's different. So here's a classic error problem with monolithic storage, is that there's no concurrency built into the application. That is, if I open up the to-dos on my phone and then I open up the to-dos on the iPad, what happens is I might get an error like this where it says it's locked and it can't read from it. And that's because Google Drive is responsible for handling the concurrency, not what the app was programmed to do. And then we have to, we're at the mercy of however that works. So you probably have seen this before in Microsoft Windows where you open a file and somebody else already has the file open. And it's like, oh, what do you want me to do? Somebody else has this open. I can't copy it. I can't edit it. I can't let you edit it. So to get around this kind of problem, we have to do a true scale up. And scaling up basically says we want to take an application and redesign it so it can serve more users. And specifically, there are two ways to scale, scaling up and scaling out. We're not going to deal with scaling out here. We're just going to talk about scaling up. Scaling out is much more complex and is really a more advanced concern, and we're not going to sort of address it right now. So when we scale up, there's two ways to scale up. You can throw more resources at the problem. That is, you can take the computer you have and upgrade it, give it more RAM. If you're doing it in the cloud, you can just usually slide a little bar and just pay more money, and now you've got more resources that'll run faster for you. Another way that you can scale up, which is a harder way, is you redesign or re-architect your application so that it is capable of being layered. That is, part of the layers, like for example, maybe the presentation layer and the business logic layer, they run together. And then over a network, you have another part that does just data access and database. And you have now separated the clients from the server. So let's talk scaling up here. So we redesign that application to support multiple users by breaking it up into layers. So you have the monolithic application over here, and then we scale it up. And what you have now is two layers. You have all the clients, maybe have the presentation and the business logic. And then down here, the server just has the data access and the database. And that's a scale up. So rather than having all the clients have all this stuff, we have now split it. And now for the client to talk to the server over a network, they need to share a protocol, right? They need to have a way that the code in the client and the code in the server can talk to each other, right? You don't even need a programmer to understand this, right? For whatever the code is in the client and whatever the code is in the server, for them to be able to communicate, they have to be able to talk on the same. They have to be able to talk in the same way. So we call this middleware. And middleware is software that would exist here in the client and here in the server, so that when they're speaking a language over the network, whether it's the internet or whatever, they know what they're saying. They know what each other is saying. Well, as the old adage goes, breaking up is hard to do. When you separate an application into parts and run them separately over a network, you now require a means so that they can communicate. So I have this split between the clients and the server, as I showed you in the other diagram. When they talk to each other, they need to be able to understand each other. So, for example, hey, data logic layer, I would like you to save this new order for me. Okay, whatever protocol the client uses, maybe somebody wrote it in Python, it's got to communicate over a network that information. It's got to say, hey server, here's an order, here's some data, this data is an order, and this is what I would like you to do with that order. It needs to communicate all that information to the server, and then the server would then do as it was requested, and then report back to the client. Maybe the server's written in C. I don't know. It doesn't have to be in the same language. And then the server would say, hey, okay, business logic, I saved this order for you, and this is the order ID of it in case you need to reference it later. And then the client would then do whatever. One responsibility of the server is to know which client it's talking to. So as the client connects to the server must respond back to the same client. This is a function of middleware. Okay, and when you hear the term middleware, this is what we're referring to. And middleware is basically software that facilitates the communications between two layers of the application. It is required whenever we split an application into layers over a network, and there are different types of middleware. for access between the different layers. There's database-oriented middleware, there's presentation-oriented middleware, there's more generic middleware that serves a lot of different types of purposes. For communication between any two layers, the layer must use the same middleware, and the layers must be programmed or configured to understand that middleware, or else they're not going to be able to talk to each other. That's basically what's going on here. So there's a lot of alphabet soup with middleware. This is where we get into all these little different terms. So ODBC is a very common database middleware. Open database connectivity. It is a means for a client to talk to a DBMS. And every ODBC middleware has a driver. So for example, if I had some client on my computer and I wanted that client to be able to talk to Microsoft SQL Server, I would need Microsoft SQL Server to be able to understand the ODBC, which it does by default. And then I would need that client to have the ODBC software on it and then be configured to connect to that server. And then once I have that, they can talk to each other. And this is basically what you see out of Azure Data Studio, is Azure Data Studio will talk to SQL Server over ODBC. There's also Corba. Corba is a business logic to business logic type of middleware. ODBC is a business logic to database middleware, or data logic to database middleware, depending on where you're at. REST is an HTTP pattern, so it's used over the web as a web protocol, HTTP, and it's used for generically invoking a service and then getting back results from that service. So it is a form of middleware, although it's not as formally written as you would see out of ODBC or Corba. So SOAP is a very formal version of doing the same thing that REST does, except it needs to have like all these additional signatures and things like that before they will talk to each other. They have to sort of be accepted by each other, whereas REST, anybody with the endpoint and the right set of credentials can invoke that. And then OData is a layer on top of REST where we support create, read, update, and delete. So it's sort of like, for databases, for tables of data, if you will, but it follows sort of the REST framework. So let's talk two-tier client server. In two-tier client server, the application is split into two parts, separated by one layer of middleware. This makes the application multi-user and multi-site. Common architectures in the pre-consumer internet eras of the 90s used the client server model. Now, I just want to point out that the business logic does not all have to be in the client or in the server. Normally, there is always some business logic in the client and some business logic in the server. This delineation is not as cut and dry as you see here. When I have this diagram, what I'm referring to is the majority of the business logic exists here. Okay, but in reality, there's always some business logic in the presentation layer in the client, and there's always some business logic in the server. And this makes sense because the cost of sending data over the network can be somewhat extreme. If I go back to that example where I'm taking photos of checks, right? One way that you can write that application is the code on the phone does the part where it reads the picture of the check and then extracts out the numbers from the check. Okay, that would require the business logic to be in the client. Another way to write it is to write it where you have the picture gets taken and then the raw picture gets sent to the server, and then the server does all the stuff where it figures out where things go. So one incurs sending a picture over the internet. The other one incurs just sending little bits of data over the internet, right? So there's a trade-off. Are you sending a whole picture over the internet or just little, like this is a $100 check over the internet? That's number one. And then number two is, how fast are people's phones? Are the phones capable of doing this on their own, or are they just not powerful enough to do that? In which case you have to send the whole picture over the internet. So these are the concerns you have when you start to distribute an application. You have to think about architecturally what makes sense. And the reality is it's not as cut and dry as even these two pictures are going to depict. It is very much a blurred line depending on each of the applications. You might have the phone just send the picture because it's not intensive enough to be able to figure out what are the numbers on the check. But then on the other hand, you might have some other data logic happen right on the phone, or business logic happen right on the phone, because it does make sense to do it there. So thin client means most of the business logic, not all, but most of the business logic exists on the server. So the only thing you get at the client level is presentation and maybe just enough business logic to sort of make things sort of simple. And this ends up giving us very lightweight clients. These clients at this end are very, they're usually commoditized, which means I can distribute several clients the same way. They don't need to be upgraded, usually because the payload for the presentation is sent from the server to the client. Contrast that to a fat client, where most of what the application does is in the client. You would have to have everybody download this client and then install it on their computer and run it, right? Or you might go to the App Store and install it, and then once you have it on the App Store, you're using it. And then people would have to keep track of what version they were on with the fat client and upgrade it. So one person might be using version 1.1, and then everybody else might be using 1.2, and you might have to find out which version's on. One person's on 1.1 and tell them to upgrade. So there's a lot more maintenance involved in a fat client than a thin client. The advantage of a fat client is you're leveraging the resources on the client and not so much on the server, right? So if you're company XYZ and you're paying for the server, then you're passing that on to the clients, right? They download it in the App Store and it runs on their phones, right? The disadvantage of fat client is some things just don't work well on the client, and it's harder to maintain the stuff on the client because there's several copies and versions of it. So, thin client, fat client. Let's talk about some examples. So if you're playing a video game like like Madden or Fortnite, those are examples of fat clients. You download tons of stuff to your PlayStation or your Xbox so that you can play that game. Now you're playing the game with other people, so obviously there's multi-user aspect to it and concurrency, and there's data, right? The maps and things like that, and the scores, and when you're running a season and stuff like that. So there's all that stuff is there. It's just the majority of what's happening is happening on the client. As opposed to a contrast of that, which would be a thin client, which is playing a game in your browser, right? Or Gmail, right? Gmail is an email, client and server. It's all in your browser. And you contrast that to Microsoft Outlook, which you download and install on your computer, and then it talks to an email server, right? So there's thin client, fat clients. Usually fat clients are more feature rich because they have a lot of that business logic built right into them, as opposed to thin clients, which may not be as feature rich. Now, the advantage of thin clients is you can take advantage of the cloud, right? So there's a lot of cool features in applications like Gmail that you don't find in Microsoft Outlook email. For example, Gmail's really good at spam detection because it's using everybody's Gmail account to do that, and there's there's millions of Gmail mailboxes, whereas opposed to Microsoft Outlook, your company installs the server for that Exchange server, and then you have the Outlook client on your laptop and your phone, but there's so few clients that you don't get to take advantage of the spam detection. All right, so let's talk three-tier client server. In three-tier client server, we have now divided up the application into three tiers. So we have a client tier, a server tier, and then another server tier that just has the database in it. And you can see there's some business logic in the client and there's some business logic in the server. In three-tier client server, the application is split into three layers. This is multi-user, multi-site, scales vertically better than two-tier, right? So you can have, everybody in your organization installs some software. That software talks to this server. That server talks to this database. The server's on one computer. The database is on another. You're now dividing up the responsibilities so that things maybe work a little better. Each layer is going to need middleware. Usually in 3-tier, the majority of business logic is still on the server. So this was a common architecture during the internet boom, and we saw this a lot in web applications where the browser itself ends up being the presentation layer, right? It uses HTML, CSS, JavaScript. It will do some little business logic with JavaScript. It draws the web page with HTML, CSS. That talks over HTTP to a web server, and the web server receives the request. It's like the endpoint of the middleware, and then the actual code that runs on the web server is the business logic. So this might, for example, let you view a particular article that someone posted in WordPress. And then the data logic talks to a database, and that database has the actual articles and the posts and the comments and all the things that people are saying about the particular blog article that's been posted on the website. And the data access layer is code that talks to the database. And so basically that's how most web applications were designed in the early ages of the internet when we were scaling things up and building web applications. You'd have the client be the browser, and then the server would be a web server that's running some code, and then on the back end you'd have a database. And this could be expanded umpteen layers. So in N tier, you're just dividing up that business logic even more. So you might have a browser, but the browser talks to a web API, and then that web API that talks to a service. So you've split out this web layer you had here. This server now got split into two other layers. One that just addresses stuff over the web, and then all of this stuff would be in your data center down here as part of the N-tier model. So the problem with going to N-tier, and the thing we learned as we moved our applications to N-tier, is wow, there's a lot of communication that goes on between all these different layers. And it doesn't help that I might have multiple clients. I might have a browser client and a mobile client, and then a client that runs on Windows and another one that runs on Mac. And boy, that's just a lot of inter-process communication. I might have specific branches of services. I might have some business logic that deals with ordering, and then I might have another set of business logic that deals with credit cards. And it's just a lot of inter-process communication. This is where the Enterprise Service Bus comes into play. The ESB, or Enterprise Service Bus, is a software application which manages communication among the independent systems. It's like taking that middleware and turning it into a service, and then standardizing on that middleware, and then saying everybody who participates in my application is going to use the same middleware and talk to the same system to manage your communication amongst the different layers of the application. I don't care what layer you're in and who you're talking to. So it provided a consistent messaging API and guaranteed delivery, and it serves as a backbone replacement for all the different messaging layers in N-tier applications. And we would give this a name called service-oriented architecture, because you would design your data application to use the Enterprise Service Bus. What's kind of neat about an Enterprise Service Bus is the one Enterprise Service Bus can serve every application in your enterprise. That's why it's called an Enterprise Service Bus. So the messaging that the Enterprise Service Bus handles could be used across not only this particular application that you're looking at, but also 4 or 5 or 10 or 15 others as well. And it handles all of the messaging concerns. And generally, the way an Enterprise Service Bus works is it's like a big message queue, if you will, with channels. And so, or topics as they're called. So this website, for example, and this mobile app, they might say, well, I need to get, the website, it might have code. Somebody might click, show me my order history. My name's Johnny. I logged into the website. Show me my order history. Johnny clicks a button or whatever. that message is sent to the enterprise service bus. It says, dude, whoever is responsible for showing this guy his order history, please pick this up and do something with it. And so that might be handled by this part. And it says, oh, that's me. I'll do that. And then it does its work. And then it says, okay, now I'm going to send this back. And this guy is now listening, waiting for a response from somewhere on the bus, right? This guy is not talking directly to the back end. It talks to the bus. Everybody talks to the bus. And so it says, I'll wait, whoever you are, to give me back what I need. And then, this guy over here says, all right, I figured it out. These are the 4 orders in this person's order history. And then it comes back here, and then it gets displayed on the website. So that's sort of the idea behind the enterprise service bus, is it decouples the end-tier application. This is tightly coupled, right? This middleware, this talks directly to that. This talks directly to that. This is loosely coupled because the different parts of the application never talk directly to each other. They just talk to the bus, and the bus talks to the other back-end architectures based on at the request of whoever's whoever's putting the request into the bus. So let's do another example really quickly. Maybe I want to buy this. So somebody clicks the buy now button and it automatically charges their credit card, right, and sends them an email, right? Or let's say it automatically charges their credit card and sends them a text message that says, "Congratulations, you just bought something," right? So they hit the buy now button. That sends a message that says, "Hey, application, buy this coffee cup," and then maybe this back-end logic picks it up and says, "Oh, that's my job. So, okay, buy the coffee cup." It says, "Okay, but before I buy it, I need to send something to the bus that says, please run the credit card and make sure it gets authorized." So maybe that goes in, and then an authorized payment service grabs that, and then it says, "Okay, that person I can charge their card," and I did, and they just got charged $20. And then that goes back, and then this would pick it back up and say, "Oh, yep, they charged $20. Good. Let's send them a text message now." And then this guy says, "Oh, somebody just said they want to send a text message. I send the text message." This business logic up here has no context of why it's sending a text message, for example. It just sends a text message. That's what it does. So that's another advantage of service-oriented architecture, is you can separate these concerns out, loosely couple your application, and help it scale. The challenge of service-oriented architecture is things are getting complicated rather quickly. So the internet ushered in major changes in application development. What we discovered is that we can use standard protocols like the HTTP protocol and then bundle our own services on top of the HTTP protocol. The same protocol that we use to show a web page, we can also use to invoke functions remotely over the web with RPC. We can also create tightly coupled messaging or loosely coupled messaging with SOAP and REST. And that allows us to really divide up our layers into very, 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 very tiny single responsibility services. So I might take that business logic and explode it out and say, this one thing, orders, you're going to do it. And that talks to a DBMS that just does orders. And then this one thing, customers, you're going to do it. And that talks to a completely different DBMS just for customers. And now you can also split out the data as well as the business logic into several individual components. And they all communicate with each other through inter-process communications with a publish-subscribe model similar to an enterprise service bus. Okay, so when you're talking about microservices, you really need to hunker down on the responsibility. So you might have business capability responsibilities, like you just deal with customers, you deal with order, you deal with inventory, or messaging capability, like your job is to send emails. Your job is to send push notifications. Your job is to send text alerts. Or there might be functions as a service, like your job is I'm going to give you a video and you're going to convert it to a 1080p 60 frame per second MP4. Or I'm going to give you a Word doc or Excel sheet and you're going to turn it into a PDF. Or I'm going to give you a video and you're going to closed caption it. Or I'm going to give you a customer and the time of day and the weather outside, and you're going to tell me whether or not this customer is likely to buy a particular product. It'll execute a machine learning function. So that ends up being how microservices works. Rather than embedding all of this stuff into some middle tier somewhere, we break it all out into its own bit and then have each of those bits communicate with a messaging application, and the messaging application in turn then handles the responsibility of routing the request back to its responder. So in a microservices architecture, you might have some clients, and they talk to maybe an API, and that API would be consistent across the mobile app and the browser. And then that API is broken up into bits depending on what kind of logic it's doing. And this API would then be talking to services on the back end, and then those services would in turn be talking to their own databases. And this is just one way that you can implement microservices. Another way that you can implement microservices is like this. You can have a mobile app and a browser-based app, and the browser-based app has a web server, and then the mobile app has an API. And then each of the API and the web servers, they in turn talk to their own individual services that deal with a facet of the application itself. Now, how these choose to talk to each other can occur in a variety of ways, and microservices does not make any differentiation between how they can talk. They can talk over HTTP REST, over ODBC. They can use an enterprise service bus if they want or need to. There is really no fixed or standard way. Now, there are some frameworks out there that are now starting to innovate this and recognize that maybe we do need to trivialize the messaging aspect of microservices a little more. But as it exists right now, it's sort of like a wild, wild west, and you can really do it in any way, shape, or form that you feel is necessary to sort of get the job done. What we didn't want to do when we first conceived microservices was to replicate what we were doing with service-oriented architecture, which was extremely message passing happy, and we wanted to sort of avoid that and use some of the best practices that we had and some of the simplicity that we had way back here in the N-tier model, right, where this is probably just talking ODBC to that, and that's probably just talking with a REST protocol. We wanted to leverage that, but also gain the flexibility that we got from the service-oriented architecture model. And together, we wanted to take those and come up with a model that sort of hybridized both of those together. And that's sort of where the microservices architecture comes from. And remember, each separate service is responsible for its own capability within the application. It is important to separate out these responsibilities. And as an application where this works for you is you can upgrade the features of the account service and not necessarily have to worry about touching the inventory or the shipping service. All right, let's finish up with our last section where we talk about the development of database applications. As you recall, the database development lifecycle really focuses on designing a database from a data standpoint, modeling it from a data standpoint, and then implementing it from a data standpoint. And then usually when you get to this point where you've created your if you're doing relational, you've made tables, and you have some sample data, you're at the point now where you might want to go back and think about how you're going to build that application. Now, the issue with taking that approach is you haven't really taken into account any of the user's needs. So normally during analysis, as you're collecting and building a conceptual model, you also might establish a set of requirements that you know are going to go into the user interface and the business logic of the application. So then dealing with the presentation layer and the business logic layer in that approach. So we know we take this model first approach, right? And we focus on data and we build our models out, but we really need to think about our other functional requirements that are captured. And the way that I like to do this is using user stories from the Agile modeling method. And they help me to identify during the analysis phase who these key stakeholders are, what their roles are, what features they require of the application that we're building, and what is the necessary functionality from a presentation layer standpoint, and what is the necessary features from a business logic standpoint. And also focusing on not what I think belongs in there, but what actually belongs in there, because I've actually talked to users. And that's important, because you can actually over-feature an application and build things that don't ever get used. And that's something that you really want to try to avoid when you're taking a rapid application development approach. So what is a user story then? A user story is basically a high-level functional requirement which focuses on a capability of a user within a system that you're building. So you're building a database application. What capability does that user need within that application? And it should contain enough information so that anybody who programs this story can do so trivially and with reasonable effort. So remember, we're going to be using like a no-code, low-code tool. So, you know, if the user story is something like, I need to be able to take a photo of a check and then extract out the amount and the routing number from that check, right? Conceptually, that's easy enough to understand, right? And it should be able to be programmed with reasonable effort, which means there's got to be some tool out there that helps us do that. There's two kinds of user stories. There's a formal and informal user story. Informal user stories, you know, just kind of match the requirement. Like you might say, a user of a web banking application needs to be able to take a photo of their check and have it, you know, deposit into their checking account, right? A formal user story is of a very specific syntax, and each user story should be written either by a stakeholder or at very least should be written with the assistance of that stakeholder. So let's take a look at some informal and formal stories. As an informal story, you might say, hey, you know, students should be able to purchase an annual parking pass online. Okay, definitely a functional requirement. The way you formally represent this user story is with the following template. You say, as a role, I can capability so that, and then receive benefit. So you might say, to rephrase this informal user story as a formal user story, I might say, as a student, I should be able to purchase a parking pass online so that I can drive to school. Now, it's important to rationalize the benefit, because this benefit helps us understand priority and value that the user story brings. If you have no benefit, then why is it really some capability you should be adding to your system? It probably doesn't make sense that it should be added to your system because you cannot rationalize its value, right? So that's where this benefit part actually is probably the most important part of the story. So many requirements we write like this, but we don't necessarily rationalize why it's important. And purchasing a parking pass is important, because if you can't purchase a parking pass, then you don't have a parking pass, and then you can't park. And if you can't park, then you can't drive to school, which means you have to find some other way to school, right? Okay. So let's do some examples here. Here's two user stories. So imagine in FudgeMart, our fictitious e-commerce company, we want our managers to be able to process vacation requests. So as an employee, I can submit a vacation request so that I can use my earned vacation time, right? People are awarded vacation time. They need to be able to use it. Seems reasonable. But we don't want everybody just saying, I think today I'm going to just use my vacation and, you know, leave you guys hanging. We want them to formally submit a request so that we have a record of it, right? So this is the story from the user standpoint, right? the person that's submitting the request, why are they doing it? Because they earned that vacation time, they want to use it. Likewise, as a manager, they can review and approve a vacation request so that their employee can take their earned vacation, and also so that they have a record that the employee submitted the request and that it was approved. If they need to go back and plan out their schedule, they can say, well, so-and-so is no longer available this week because they are on vacation. So there's a lot of benefits here. I just sort of trimmed out the benefit part of it to make it fit on the screen. All right, so here is an application running on the right, and this satisfies that first user story. So this is an example of user interface. It's forms over data, right? The data model is pretty simple. One user can submit many vacation requests, and this is just the user interface that supports submitting a vacation request, right? So I go to vacation requests, I hit new request. Up here, I type in whatever the reason I need the request. I'm going to France, and then who are you? Pick your name out. When are you going to France? How long are you going to be in France, right? That's just everything I need to capture for that. That's part of the data requirements, right? But I've built a user interface around the user story. So here's that same user story from the manager's perspective. Here's the manager's user story. They need to be able to go in and review the request that somebody made and approve it, right? So that they can give that person their earned vacation. So, for example, I would go in here, I'd click on vacation requests, and then I'd go to pending requests. Then I'd find microphones request. There it is. I can review it and then hit approve if I want. And then who approved it? Me. Only the manager showed up in that list. And then I save the request. Now, granted, there's probably a little more to it than this. I probably want to have a approve and then a not approve. And if I don't approve, I probably want to have a reason. But again, this is just a very simplified example that I'm showing you to give you an idea how a user story might map to features. You see that you don't have to get too far into the weeds as far as design goes, because the data requirements sort of determine the kinds of information that you're going to have in the user interface of the application, and therefore there doesn't need to be a lot of effort spent on the details of the design. So this is something that is very common among data-driven, database type applications. Because we are so model heavy, there does not need to be an extensive amount of work put into the presentation layer and the business logic layer. It tends to be rather trivialized by the underlying data model. So let's sum up this unit. Database applications are data-oriented applications that can be developed usually with no-code, low-code tools. They take a model-first approach, and because they take a model-first approach, their business logic and their presentation layers sort of directly correspond, if you will, to the data model, or closely correspond to the data model. And because of that, we can use these no-code, low-code tools to build these kinds of applications. These sort of applications are called line of business applications, forms over data applications. Those are usually common names for them. Database applications are divided into layers, presentation layers, business logic, data logic, and database. And not only database applications, but all applications are divided up into these layers. And the database applications come in a wide variety of architectures, from monolithic to microservices. And when you're building a database application, if you use a monolithic architecture, that governs the accessibility of what the users can do and how the data is stored concurrently. So maybe it's not a good fit. And if you go microservices, that adds a lot of complexity, but sometimes you can get around that complexity by using a cloud service that gives you all of the capabilities of microservices, but not all of the worry and pain of you having to figure them out. And then finally, we use user stories to capture presentation and business logic concerns for our database applications. We don't have to worry about the data concerns because we're capturing those in the conceptual and logical modeling. That's basically